Okay, fine. Is my voice echoing or is it okay now? Am I audible by the way?
Yes, sir.
Audible, sir. Audible.
Okay. Sure. Yeah, it's recorded, Vivek. We are doing the recording. Currently, the live streaming is not working since last few days for most of the courses. There might be some problem on this G Suite side. Yeah, so we are recording
Okay.
it. Update it after some time.
Okay. So yesterday's session was also recorded because I was trying today and I couldn't see the YouTube link.
The thing is actually the sessions after recording they come a little late.
Hmm.
So once it comes, we would update.
Okay.
Oh,
So
by the
I'll.
way, yesterday was that TA discussion, right? I mean the programming assignment discussion, right? You
I
mean?
don't know. I couldn't attend it, sir. So I
Okay,
don't
fine.
know.
So yeah, so there would be one discussion every week. It was in this week only. It was on the previous day, but from now on, every week it would be on Thursday, and that discussion Thursday from 12 to 2, and that would be specifically for programming assignment, practice programming assignment discussion.
So which week was it for yesterday?
So that was, I think, week 5 was discussed, most probably. I don't know.
Oh,
I am not sure.
okay.
Okay. So
Okay.
most probably week 5 would have been discussed. But it would, the thing is, since this session would be only for discussing the programming assignments and specifically the assignment, practice assignment mostly. So these sessions would not be recorded. So you have to, I know it's at a odd timing, but there were no better timings also. I mean, there were no available slots.
Okay.
So,
Right.
so we had to do it at that time. You can attend it if possible. So those would not be recorded. We would try to do something maybe from next to next week if there is a possibility of streaming them. But as of now, for this week and the session that already happened, these two sessions, like from Thursday, there would be one session tomorrow. So
Right.
tomorrow's session and yesterday's session, these two sessions are not recorded.
Okay. Right, sir.
Okay, fine. So, by the way, how was your exam? Any suggestions?
It was easy, sir.
Was easy? Great. Fine. No one else is telling anything now. Since one guy has already said it was easy, so no one else would say anything other than that. That is sure.
Yeah, it was kind of easy only. Okay.
Accept fine. Okay. Great then. So now after main contents would come this graph and more difficult. You can expect quiz 2 to be a little more difficult. All of you. So be prepared for that. And today we would discuss week 7. So balance history. By the way, before moving into that, are there any general doubt in week 6? I hope heap was properly discussed in that session about pseudocode and all those things. And only thing that was left is using that those functions which we understood in that particular session, right? The heap function, extract main, okay, all those things. So to use those functions inside the Prim's algorithm and Dijkstra's algorithm to bring down the running time from a quadratic one to a logarithmic one, n log n kind of complexity. So that was the only thing left. That I think a little bit of that might have been discussed in the subsequent session. But yeah, so those things are clear. How Prince and Dijkstra using the heap. Most of you would not have seen.
Sir,
Yeah, any comments?
there was no subsequent session after that, sir. The last one was what you took the last time.
Okay, so in the live coding, in the revision session, those things would anyway not be discussed. But before
Yeah.
that, there were no more session, right?
No, no, sir.
Sure. Okay, anyway, so let me do it in this way. Since those two things are just application, right? Only applying the heap concept. in Dijkstra and in Prince, I also showed that 1-2 line of code where you apply that in that session itself. So I would still discuss the whole code, just the application part, since it's kind of an application. I would discuss it in maybe one extra session we would have this week. I don't know when we would have it, but we would have one extra session. In that session, briefly, I would discuss that. And along with that, I would discuss a leftover part of week 7. So those two things I would discuss together in an extra session this week. We would inform you when that is scheduled. And today's session, I would try to cover the aerial tree, this balancing tree, binary search tree, all those things together, because that is something again a new topic. That Dijkstra and Prince algorithm using heap is an application. So, I mean, if you have gone through that live session, you are already clear with the concepts. Now you just have to apply it. So it would not take a lot of time. But today's concept is much more, again, a new data structure, so you would learn a lot of things. So I would complete it today, and in an extra session, we would discuss week 5, those two part, application part, and I think union find was also left. So union find, those two applications, and some leftover part of week 7 in an extra session. Fine. As of now, we would discuss the first lecture of week 7, which is balance trees. Sure. My screen is visible, right?
Yes, sir, visible.
Fine. Okay. So let's say at first, what is a tree? So we have discussed as a part of our heap, right? That what are trees, and also we have discussed what are binary trees. Okay. Now, if I say what is a binary search tree, or in short BST, what is that? What is a binary search tree? So tree we know, tree is something, I mean, if you have, let's say, I mean, this parent-child kind of thing, right? So this is what you know of tree. But actually the formal definition of any tree is when you have no cycles in a graph, then you can call that a tree. Or more formal way to state that is, let's say if you have n vertices in a graph, then in order to connect those n vertices, you only use n minus 1 edges, right? If you use n minus 1 edges, you can be sure that there are no cycles in that graph. So then you call that graph as a tree. So that is a formal definition. A graph with n vertices and n minus 1 edges, which inherently will not have any cycle, is what we call a tree. But in our problem solving perspective, we have seen that a tree basically visually looks like a structure like this. And we have learned only about binary trees, which essentially means that there would be two children, at most two children for each of the node. Either it can be zero for like say the leaf node, they have zero children, and let's say all the internal nodes have two children. In this case, if I have one more guy over here, so that means this one is actually a one children node. And we have also learned then if what is a heap. A heap is basically a almost complete or mostly complete, whatever, almost complete binary tree. So remember, this is binary tree. Okay. Now, what is a binary tree? We have learned that almost complete means this last level is not full, right? This last level is not full. Ideally, if we have all these nodes, right, in the last level, all these nodes, then we would say that this is a complete binary tree. But even if I do not have the last level filled up completely, then also we would call it a heap, and that's why the definition of heap is almost complete binary tree. Now, that was the idea of binary trees. So mainly they are called binary because they have at most 2 children. Now we learn about what we call binary search tree. Okay. Now what is a binary search tree? A binary search tree is any binary tree. The only extra criteria over here is that you insert the element so that it has some property with respect to the siblings. Now what do I mean by that? So in a heap we learned about, if I, let's say I am considering a minimum heap, so whatever parent value is there, the child value can be greater than that, should be greater than that, right? But it cannot be equal to or less than that. Okay, so if I have, let's say 10 and 12, again over here I have, let's say 13 and sorry, not 30, let's say 33 and 21. So I have something like this. So the only thing is the children should be smaller than the parent. But I did not have any condition among the siblings themselves. Right? That was the thing with him. The siblings had no condition. So I can have the left sibling greater than the right one, or even the right sibling greater than the left one. So in these two cases, you can see that here the right one is greater, here the left one is greater. So there is no property or constraint with respect to the siblings in a heap. Now in binary search tree, we would just introduce that constraint. In the BST, we would introduce that constraint. That we would have a relation between the left and the right child as well. Okay, and we would eliminate the relation between the top and the bottom. So parent and children, there would not be any specific relation, but left and right child would have relations. Now what is that relation? The relation is that your whatever is on the left, if I just sum it up, whatever is on the left hand side, that should be smaller value. Okay, so the more you go towards left of the tree, it should be smaller value, or more you go towards the right of the tree, that should be larger value. So if I have this kind of sibling relationship, then this left one should be smaller. Okay, and right one obviously should be greater. But the thing is, I told you the notion is not only among siblings, the thing is the more left you go towards the tree, more left you go towards inside this tree, you become smaller and smaller in value. The more towards the right you move inside the tree, you become larger in value. So even if I consider 5 and 10 over here, right, I can see, now don't think the height, okay? So in binary search tree, we just consider we do not consider the height, we do not consider the parent and sibling, all those, parent and child relation. We consider this horizontal relation, which one is on the left side, which one is on the right side, respectively. So let's say 10, not respectively, relatively. So 10 and 5, if I just consider from the perspective of left and right-sidedness, so 5 is right-sided of 10, right? 10 is on the left-hand side of 5. So this is a heap, mean heap, proper mean heap. But this cannot be a binary search tree. Because binary search tree says, as left, the farther left you move, your value should become smaller. And the farther right you move, the value should become larger. So if I see from top, right, if I have my eyes at the top, right, over here, let's say I have my eyes, fine. Then my perspective would be, I would not see the height, correct? If I see from top, I would not see the height. Only if I see from one of the lateral side, then only I can see the height. I mean, this height between 5 and 10. So if I see from top, I would only see the overall placement. I would see that 10 is a bit left, then 5 is there, and then 12 is there. Okay. So this structure can never be a binary search tree. This is a invalid, this is not a BST, because 5 is towards right and it is smaller than the left one, which is 10. So the thing is, now I would just give you an example of a binary search tree. So let's say I have 8 over here. I would insert a smaller value on the left hand side, let's say 6, and here let's say further smaller value, let's say 4. Okay, and from 6 I would have 7 over here. Okay, and let's say 9, and let's say 10.
Are you people getting voice breaks, or is it only at my side? Because in between voice is breaking for me.
Okay, is anyone else facing that?
No voice break.
It is continuously you people are able to hear?
Yeah, at least I am.
Okay, then it will be my side only, because I am getting in between, like a few seconds it breaks, then it comes clear again.
Maybe due to some network problem. I think from my side it should be fine. Let's check.
Voice is okay. Okay. Voice is okay.
Okay, okay, fine.
So I have
Yeah,
one small
Huh.
doubt before you
Yeah,
carry on
Vivek.
with the binary search tree.
Yeah.
In heap, if we come to the first diagram of the tree, you put
Okay.
5 and their 2 children, 10, then 33, 21, and 12.
Huh.
I just have one doubt. Below 10, if I have 11,
Huh. Okay.
is that will that be a
Heap.
heap? Yeah.
Yeah. So let's do it. You mean something like this? If I have it's 11 and whatever 21.
Yeah, because 11 is less than 12.
Correct.
So if we are going with a minimum, so where the heap is only concerned with that particular branch,
Exactly.
right? Right.
Not only
Okay.
branch, it only considers the parent. That's
Parent.
the thing.
Okay. 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 So the other side of the parent, the
No,
right side is
nothing.
not considered. Okay.
No, no. If you remember, the Heapify
The
algorithm
heapify,
was the
yeah.
crux, right? The
That's
Heapify was the crux. Heapify
exactly.
was only dealing with 3 elements all the time: left, right,
Right.
and root.
Right. Sir.
So yeah, so if I draw a tree like this, now this is again a binary tree. You can see that all the nodes either have 1 children, 0 children, or 2 children. So first thing is this is a binary tree, that is for sure. Now the second point is, I would see that is there any specific relation that I promised among the siblings. So if you can see from here that take any possible pair of siblings, okay? You see, let's say 4 and 7. You see 4 is smaller, the left one is smaller, 7 is larger. Let's take 6 and 9 as the siblings. You see 6 is smaller, 9 is larger. Okay? Like that, let's say if I consider at one level, so let's in this level, right? In this last level. You see that 4 is the smallest, then 7 and then 10. So that thing which you just questioned over here, I mean, yeah, Vivek just questioned over here, that if I have 12 on the right tree and 11 on the left tree, but still, is it still a heap because 11 is a smaller value than 12? Now see, that property actually comes in the binary search tree, that your left and right, your sibling, whatever, all those things come in the binary search tree. So I personally like to view heap as a y-axis or your vertical axis constraint data structure, and binary search tree as a horizontal axis constraint data structure. Now, so that's why I said just look the tree from top. If you look the tree from top, right, then you would not see the height. You would only see that 4 is the leftmost. So from top it would look like something like this. 4 would be the leftmost. After then you would see 6. After then you would see 7. After then you would see 8. After then you would see 9. After then you would see 10. How many of you disagree with this? If you see from the top, you would see the tree something like this. One, right? So yeah. So that's the point. If you see from the top, yeah, Nikhil.
Sir, can we put 11 instead of 7?
Instead of 7, if can we write 11?
Yeah.
No. Why? Because see, if I put 11, suppose if I put 11 over here,
Yes.
then what does it mean? That means that 11 is right side of 6, right? Seeing from the top. 11 is right side of 6. So that means 11 should be larger than 6. Now that is okay. That is fine. 11 is larger than 6. But again, you know that 11 should be smaller than 8 because 11 is on the left side of 8. Not getting it? Why 11 is on the left side of 8? Because see, if I draw the structure properly, 8 at left hand side you go, then you get 6. And then you come a right hand side over here. Okay, you do not say that once you have moved left, you cannot go like this to the other side. Okay, so once you have moved left, you would remain on the left. So this whole tree would remain on the left hand side of 8. And this whole tree would remain on the right hand side of 8. Okay, so we draw with pen so it looks something like this. But if you correctly draw it, then the tree exactly looks like this. So this gap must be very much like 6, like 4. Then you have here 11. Then here you have 9. Sorry. Then here it is 10. Okay. So you
you
see
can say
11. Yeah.
So you can say that everything to the left of 8 will be below 8.
Smaller than 8. Correct.
Okay.
Yeah.
Thank you, sir.
Okay. So 11 is.
One more.
Yeah.
In tree, you don't have to go by left to right because below 9 you have gone to a right side of the 9. So it is not a must that you should fill the left side first.
Sorry, which one? 9?
Below 9, you have drawn the right side as 10. So is it
Uh,
not necessary the binary tree should have the left side also? Then we go to right side? Not necessary.
okay, yeah, no, yeah, good question. Thanks for reminding me that. So that was the property of heap, that you always fill up the one by one. Take
Yeah.
the, yeah, so in binary search tree, that's not a constraint. So
Okay.
you can fill it. But I would also discuss how things are inserted in a binary search tree, then that part would be much clearer.
Okay. Just to know
Okay.
about binary tree, I just asked this question.
No, no, please, yeah, good. Yeah, that's
Yeah.
important.
Yes.
Forgot to mention. Okay. So here we do not consider that I must have an element in this point before having an element 10, right? Like in heap, it was compulsory. In heap, you cannot insert a 10 like this without skipping this part. Okay. So this is compulsory in heap, but here it is not required. Why it is not required? The
Sir, here
insertion. Yeah.
in 9, if you put 10 there, then 10 is greater. So you have to have less than 9 on the left hand side
That is
for
not
9.
possible in this example. That is correct. Yeah.
Right.
I must have a smaller value which is between 8 and 9 over here, because this part is right hand side of 8 but left hand side of 9. So I cannot have a number, an integral number at least in this position. But yeah, the thing is, the idea is that you can, it's not required, it's not compulsory to fill up binary search tree like heap. You may not need all the positions. I would come to the insertion, how we insert element, then it would be much clearer. But now the point is, the property of a binary search tree is that it should be, as the more left you move, the smaller elements you see. So according to that concept, if I say which would be the smallest element, obviously the leftmost element would be the smallest element, and the rightmost element would be the largest element. Okay, in a binary search tree. So this is binary tree was any tree which has two or at most two children for all the node. And when we are using this not sorted, I mean this property of left child must be smaller than the right child, right? So in that case, we add an S over here and we call it as binary search tree. Now, why do we call it binary search tree? I would come to that, but before doing that, we would now discuss how to insert an element into a binary search tree. Okay, so what are the properties, by the way, if I just formally write it, that your left child must be smaller than your right child. Some implementation take this as equal to, right? Someone is smaller than equal to right child, whatever. I mean, let's say you can have an element like this, 6, 5, sorry, not smaller than equal to, it's smaller than, it would be always smaller than right child. I mean, with the root, it can be equal. So what I mean is, the left child must be smaller than root for the parent, and third is right child must be larger than parent. Now, some implementation would consider equal to in these two cases. I mean, if it is equal to in the second case, it would not be equal to in third case. If it is equal to in third case, then it would not be equal to in second case. Okay, so whatever we generally follow, we would give you in the question, so you don't have to worry about it. And if nothing is given, then you would not get equal values. All the values would be separate, so you do not have to deal with the equality dilemma. So these are the conditions. But I told you that in binary search tree we do not consider any parent-child relation. But here I can see parent-child relation. This is not I mean, in order to discuss, I have written it in this format, but there is not that kind of parent-child relation. Here the relation is because of the location of the parent. Whenever I have a child which is left-hand side of parent, that means it is more left of the tree. Whenever I have a child which is right child of the parent, that means that child is more right hand side from the, I mean, towards right, more right hand side in the tree than the parent. Okay, so because of that left sidedness and right sidedness, we are deriving the second and third property. But the actual property is more left you go, you would get smaller element. That's the whole. Okay, so these three properties actually makes your binary search tree, and there are no other property. In heap, we had extra properties like you have to fill up sequentially, like the point raised by, I think, who raised that, I forgot, Sumit, I think. So yeah, thanks for that. If I am mistaking the name, please pardon me. So yeah, so that left filling up sequentially is not required. Almost completedness is not required. Okay, only these three properties if you follow, then it would be a binary search tree. Now on the basis of these three properties, if I ask you, is this a binary search tree? Sorry. Made a mistake. Yeah, is this a binary search tree or not?
Yes.
Yes.
Yes. Yes.
It's a binary search tree, right? Yeah. So this is also a binary search tree because it follows all the properties. Although it looks like a linear data structure and it would be essentially end up like a simple linked list. But you can have binary search tree like this. I mean, conceptually, theoretically. And that is one of the nightmares. We would come to that at the last of this topic. Fine. So now insertion into BST. Simple topic. I would just go over a bit fast now. So how do you insert element into a binary search tree? So let's say I have these elements only. If I take these elements, yeah, fine. So 8, 6, 9, 4, 11. Okay. Fine. So now if I say we have to insert, suppose 1 or let's say 2. Fine, I have to insert 2.
So
Yeah. Yeah, Nikhil.
instead 11 couldn't be there, no?
Oh, see, I took that example and I forgot to delete it. I think 7 was there. Fine. So first, let's say I have to insert 2. So how can I do it? This is the structure of the T which is already given. How would I insert 2? So what did we do in heap, by the way? So when we had a structure like this, as I mean the heap, suppose this is my heap. What would I do? In order to insert a new element, I would insert the element at the last available spot. So the last available spot is this one, in this case, right? This one. So I would insert it like this, and then I would compare this node with this node, like till the parent. Okay, and I mean provided it goes till the parent. If it does not satisfy the less than condition, then I would stop at that point. But until and unless it is, until it is satisfying the less than condition in a min heap, then I would simply swap the elements. I would swap this element with this element, and I would do that till the parent. So that was how we used to insert in a heap. Here, what we would do is, here we have one property that we know the sorted order, right? Not sorted order. You would see the sorted order a bit later. But you know that I have a relation that every left-hand element must be smaller than my current element. So whatever is my position, if I move left, I would get smaller element. So I would start from the root in order to insert 2, and I would compare whether 8 is equal to 2 or not. And you see that 8 is not, 8 is not equal, not equal to, 8 is greater than or less than 2. So you see that 8 is greater than 2. So that means if I have to insert 2, it must be on left hand side of 8, because all the smaller elements from a given element should be there on the left hand side. So I move left. I reach over here at 6, and then I see that what is 6 is there. Now 6, is it smaller than 2 or not? Again you compare and you see no, that 6 is greater than 2. So that means still I have to move left. So again you move left, right? And then you see 4 and you again see that 4 is still greater than 2. And that means again I have to move left. But as soon as you move left, you do not see any further element over here. The tree ends. So that means that you have to insert your element over here. So you insert 2. Now you see, by following this rule, you actually satisfied the sibling property. The left element should be smaller, right element should be larger, that property. If I take now another example, now let's say if I have to take 3, fine. Next I would insert 3. So again same steps, I would come to 8 and see that 3 is lesser than 8, so move left. 3 is lesser than 6, so move left. 3 is lesser than 4, so again move left. But now 3 is greater than 2, right? So whenever it is greater, I have to keep it on the right. So I would not move left. right? Because 3 is greater than 2. So I would move right and insert 3 over here. Right? So this is the tree. Now again, let's take one more example, then maybe we can stop, and that is, what should we take? 5. Okay, 5. So yeah, other than 5, there is nothing good also. So if I take 5, so again you see 8, 5 is lesser, move left. Again you see 6, so 5 is still lesser, move left. Now 4 is lesser value, 5 is a greater value. As you know that my current element 4 is lesser and the element that I want to insert is a greater one, so I must insert it towards the right side. So you insert 5 over. Okay. And by this thing, if you see again from the top, what you see, how would the data look like? See, from the top, if you see 2 would be the leftmost element, right? 2 is located at the left, towards the extreme left. And then, so how can I say it is extreme left? Just think, this is a number line, right? This moves in these 2 directions. Now you think that this is the left element, right? 2 is the leftmost element. So 2, after that you would see 3, right? After that you would see 4. Just moving from left to right, after that you would see 5, after that you would see 6. Then from moving from left to right, 7, then 8, 9 and 10. Now the beauty is you see that this is the sorted order. 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? You saw it just from the top. You did not do anything else and you followed the rule, left element should be smaller than right element. And when you actually insert in this format and you see it from the top, you see that the order that you are getting is a sorted order. And this way of traversing the graph, so we have learned about BFS, DFS and all those traversals. So you are traversing the graph, right? And this traversal is what we call the level order traversal. I mean, not exactly level order, it's actually, level order is something where you print each level by level all the element. So this is also called level order, but it is in a different manner. It is happening from top, and that kind of order is actually termed as, so in order to print this sequence, if I ask you, right, if I have to, let's say you start from 8, right, your algorithm is starting from 8 and you have to print this sequence. Now, we wrote this sequence with the idea that we are seeing from top, but if you have to really print it by writing some lines of code, then how would you do that? So the thing is, if you see that you have to print 2 first, that is the leftmost element first. Okay. So what you can do is, you can write the code like this. Let's say the function is some display function. Okay, and here we have a node. This node is essentially initially your root node. And after that, what you do is, you want to print the left side first because that would ensure your sorted order. Fine. So what I would do is, node arrow left or node dot left, I am writing in a pseudocode format, so I am writing node arrow left. If you write Python code, then accordingly you have to write it in the syntax. Okay, so what I write is display node left. Fine. Then, okay, so let me first complete it, then I will tell. Now let's see what happens in this scenario. So I'm using recursion, so not one recursion but 2 recursions, right? I say display node arrow left. So I'm going towards the left. So when I'm at 8, I would go towards the left, right? Because this line would be executed and again I would come back over here. But now my node has changed. Now my node is at 6. So I have come to 6. Accordingly, again with 6 I would come here and I would see display node arrow left. So again I would come to the same path, but now my value would be 4. Okay, accordingly, every time I come into the display function, I would go left, left, left until I reach at this point, And okay, so here I have to write the base condition. If your node is equal to none, then you return. Okay, so that is the base condition, that if it is none, then you return. So at 2, when you come at 2, node arrow left by doing that. So again, you with 2, you would go to the recursive call, and you see that there is nothing on the left hand side of 2. So my base condition would satisfy if node equal to none. Node is for, I mean, for 2's left, right? When you go to 2, the left of 2 there is nothing. It is empty. So therefore that would be none and it would return. And as soon as you return, you print. So what would be, how would happen? It would come back for 2 at this line of code, right? So what is print? Node value. So now the node value, it was for 2, right? Node was at 2 at this instance. So my node value would be 2. So 2 would be printed by this line. Okay. And then again I go for with 2, I go to the third line, which is display node right. Now I come right of 2, which is 3 now. So with 3 again I would come to my this function. Okay. And then I see that if node equal to none or not. No, node is equal to 3 at this moment. Then I see node arrow left, right? So when I go for this node arrow left for 3 again, right? So then I see that node this equal to would be true, because when I go left of 3, there is nothing there. So when I go for node arrow, so when node is 3, so 3's left would be none. So then in the next recursion, this condition would hold and it would return. Once it returns, it would come over here in print and it would print node dot value, which is 3. Okay, and then it would go for node arrow right. So again for 3 it would go to right, and again this condition would satisfy, you return. So finally the function up to this for 3 is over, and also for 2 is over, because you have print the left and right neighbor of 2 and also the value of 2. So again you come back to the position where you are before calling 2, like recursion happens, right? I would not iterate it one more time. You all know recursion. So again it would come back at 4 and then it prints. So this is essentially your simple code for printing the element in this fashion, and this fashion is what we call your in order fashion. And that's why it's all literally it means in order, right? It is in the order. So this is your in order. And if you want to remember it, whenever you display, so display is there, at first your nodes left, then you do the print node, and then you again go for display nodes right, right? So this is what we call in order. If you just swap the codes in different combination, so let's say if I write the print at first, and then I go for, let's say, display of the left one, and then the display of, I'm just writing in short, display of right child. Can you tell me what would be the output in this case? Can someone tell me what would the output of, if I run it from the 8 root node, what would be the output? Okay, so you start from 8, right? At first you print n. So your n is 8. So you print 8 at first. After that, what? You move towards the left of 8. So left of 8 is 6. Right? So then you print 6. Because as soon as you come, right, whenever you call, the function starts from the print statement itself. So whichever node you see at first, you would print that. So 8, 6, 4, like that you would do. Whenever you move left, you would print that. And then again you move left, you print that. 8, 6, 4, 2, like that. You can do the rest of it. And again, just if I swap it again, so display of left child, display of right child, and then I do the print. Right. So this is again another order. Right? Just try how it would look. So this is what we call as post order. This is what we call as pre-order, and this is your in order. Now, why is it in order? You can remember it because the print is between the left and right child recursion call. That's why it is in. Why is pre-order? Because print is before. That's why it's pre. Print is before left and right child code. And why it is post-order? Because print is after the left and right child code. So you can remember it in that format also. And you start from the root, you apply this recursion and you see different outputs. But among all these outputs, only the in-order output would be the sorted sequence. Okay, so this kind of question might come. Okay, so that's how we insert element in a binary search tree, and this is how we display element in a binary search tree, depending upon which order you want to do it. But if you want to see the sorted sequence, then it would only happen in the in-order traversal. Your in-order traversal is essentially you looking from the top of the data structure, like the one we discussed. Fine. So insertion has been discussed, and this in-order this traversal is also discussed. Now, the problem is,
What is the relevance of this pre-order and post-order?
sorry,
The relevance of this pre-order and post-order?
pre-order and post-order?
Relevance of this.
Relevance, acha.
Yeah.
So relevance of this is actually, these are used in multiple operations like, so when you convert, I mean, so we do operations like this, right? If I tell you to do, let's say 8 plus 4 minus 6 into 30, something like this, a simple arithmetic operation. So what you would do is, maybe you can apply the BODMAS rule, and according to that you would work. I mean, so let's say into happens first, and then plus happens, and then you would do the minus. So something like that should happen properly. Okay. But the thing is, you are actually putting the operators between the operands. So I would have operand 1, and then I would have one operator, and then I would have operand 2. So this is what we call your infix notation. But it seems that computers can work, I mean the way in which computer works, right? So that is not very much the way in which we do our mathematics. Computer works in a different manner. So the way in which computer works, in that way, this pre-order use or pre-order evaluation of expressions gives it helps computer to do the computation. Now I cannot go into the exact details of how that computation happens, but essentially you can have an expression tree. Okay, so if I draw it in this format, so it would be something like this. So let's say this expression, right? So it would look, the expression tree for this expression would look something like this. Fine. Now, if you have an expression tree like this, you convert this expression tree into a pre-order traversal, right? What you said, the relevance of pre-order. So if I do a pre-order traversal, I would get minus as the first element. Okay, because that would be printed at first. Then I would go left and find plus, and I would print plus. Okay, then again I go left, and now I get 8, so I get 8 over here. Okay, then I return back to plus. Okay, pre-order, so left, and then I would come back over here after printing. So again, okay, so wait, print plus and then moving left. Okay, fine, yeah, 8 is printed. Then I come back at plus. So after that I have to move right, so I would get 4. Okay, so accordingly, if you do the pre-order, whatever the in respective manner, you come back from 4 to minus, and then you go to into. Okay, and then you go to 6. And then you come back to into, then you go to 30. And finally, yeah, so that's it. So this is your pre-order result or pre-order traversal. It seems the computer can work on these expressions in much better way. So if I have to convert this human understandable arithmetic expression into an expression like this, then I would need a expression tree like this. And this tree's pre-order traversal would give me something like this. And this format of the arithmetic expression helps the computer to solve it in a much better way. Okay, now how that computer helps you to solve? In order to understand that, we have to discuss that is a separate topic. Actually, we have some questions on that, but that is a little bit exercise on your side, but not in very detail. Okay, so but if you have any doubt, you can post on Discourse. The idea is this is the relevance. This is used in internal work of computers. Fine. So now let's see if I have to delete an element from your binary search tree, how we can do that. That is another important point, that how to delete element from a BST. Okay, so let's take this tree only. Fine. So, okay, so now let's say in this tree I have to delete an element. I have to delete an element. Uh, at first, let's delete 10. Okay, so now we would say deleting. If I have to delete 10, what we would do is, let's say the easiest idea that we have, just remove 10 directly. Do not do anything else, so delete 10. What we would do is just remove it directly. Okay, what I would do is just remove 10. Now, is it still a binary search tree or not? If you see that I have not violated any condition of a binary search tree, and this tree is still a binary search tree. So that means there is no problem in the deletion of 10. The way we deleted 10 is absolutely fine. Okay, we did not make any change, just remove 10 as it is. But why we could do so? Because 10 did not have it did not have any children. I mean, 10 was a leaf node, so that's why we could remove it. But what happens if we have to remove an element which has a children? Then what do we do? Okay, so let's take an example of 2 at first. Okay, if I have to remove 9, then again see I don't have a problem because 9 is again a leaf node. So we do not have to do anything else, just remove 9. But if I have to remove 2 in this scenario, then what can I do? Okay, so then you check that whether there is a left child which is missing or right child missing. If there is a missing left child, so in case of 2, you see that there are no left child. There is only one right child. Fine. Now, if I draw the graph, this portion, just focus on this portion. If I draw it absolute correctly, I mean by placing the elements in their proper position, so it should look something like this. I'm just drawing a more accurate version of the same tree. Right? So this is how it should look. So that means that 3 is on left hand side of 4, right? From here it looks 3 has crossed 4, but whenever you are moving left, that means you are moving left. I mean, from the center of this thing, right? If you draw a center line from here, once this is a left edge, then you are obviously whatever is there, let it be anything, let it be 100 more levels, but it would be on left hand side of 4. Okay, so the ideal diagram should look something like this, that 3 is located on the left hand side of 4. So since 3 is already left hand side of 4 and I want to delete 2, I just have to keep in mind that all the element on left hand side should be smaller. So what happens if I just remove this 2 directly and replace it with 3? If I do something like this, then is this part still a binary search tree? Yeah, we can see it's still a binary search tree because 3 is smaller than 4 and then 5. So we are not running into any trouble by directly removing 2 with 3, swapping 2 with 3. So that's what we will do. We will just swap 2 and 3. I mean, not swap, I will delete 2. In place of that, I would put 3. Accordingly, let's say if I had 1, right, in place of 3, I had, let's say I did not have 3, instead I had 2 and 1. 1 as the left side. Again the same thing. Anyway, let it be 1 or let it be 3. I mean, let it be left child of 2 or let it be right child of 2. Both left and right child are obviously on left of 4. That is sure. Both left and right child of 2 must compulsorily be on left side of 4. So even if I have a single children, I would just place that in place of 2 and remove 2. Because that is, anyway, it would be smaller than 4, and in binary search tree, I just have to keep in mind whatever is on left should be smaller. So even if it is 1, I would just replace 2 with 1 and this would be out. That's it. Or if I had 3 only as one of the kid, there were no 1, then I would replace this 2 with 3 and we would remove this. So that's the idea. When I have, yeah.
Hello.
Yeah.
What if the 3 has another child nodes?
Correct. So let's do that. So I had 2 over here, 3 over here. Right? Now what if 3 has another child node? So actually in this example 3 cannot have
Child for 2 also, sir.
a child for 2 also will do that. So for 2 children I would discuss. Just just give me some time.
1.
But even for 1 children, but more than 1 level, right? Here we directly swap 3 in place of 2. But let's say here we had some other number. Now you see that after 3, 4 is there. So I cannot have any other number. But for the sake of argument, assume we had 3.5. I mean, I'm considering real numbers now. So assume we had 3.5, right? So 3.5 is large. Yeah.
This I got. But if 2 has already 2 childs and the 3 has also 2 childs.
Exactly. So, okay. So this, by the way, what we would do? If I have to remove 2, what we would do?
We will just replace 2 with 3.
And then we would carry this whole thing in place,
Yeah,
right? I would just...
yeah.
Okay, fine. Now the thing comes, let's say I have a number like this.
Yes.
Okay, 1. And let's say here also with 1. Fine, let's say this is the structure.
Yes.
Now what to do? Now I want to remove 2. Now there is the most complex case that when both your left and right child have children, I mean at least first of all both your left and right have some child, right? They are not, there is no single space which is left, right, in 2. So both you are in 2 children node. 2, I mean 2 is the node you are deleting has 2 children, and there may be a case when those 2 children also have their children, like in this case. So whenever, even if I had only 1 and 3, and this 3.5, 1.25 and 0.25, these last 3 nodes are not there, then also we would follow the same technique. And even if I had all these 3 nodes, then also we would follow the same technique. And what is that technique? The technique is, our main intent is to keep everything smaller on left and everything larger relatively on right. So if that is our intent, and if I want to remove 2, then with what number should I replace 2 with? So the thing is, this whole tree, right? This is diagrammatically, maybe not diagrammatically, but conceptually, this whole tree on the left hand side of 2, right? It is on the left side of 2, and this whole tree's all element is on right side of 2. So again, that's why I magnified this drawing over here. Just assume it in that manner only. I'm not drawing it again. So whatever is on left child, that is always located on left hand side. Always it will be smaller. Doesn't matter how many levels you go down, it would be smaller than the 2. Right? So even if I go 1.25, 1.55, 1.75, 1.85 like this, if I grow like that, but still that would always be smaller than 2. Now diagrammatically it may look it is moving beyond 2, but if we draw it properly, then obviously we would draw it large like this, and then we would have 1, and then 1.25, 1.55, 1.75, dot. Okay. So that's the idea. So fine. Now let us discuss the main topic. Now how to do it. So the thing is, we have to replace here with a number which is smaller than 4, right? Smaller than 4. And how can we do that? So there are two options. Either you know that this left subtree is smaller than 2 always. Okay. So if I put the element, right? If I put the element which is your largest, then which is the largest in this subtree, right? If I put an element which is the largest in the left subtree, and which is the element, what's the element which is largest in this left subtree? It is 1.25, right? 1.25 is the largest. So let us see what happens if I put 1.25 in place of 2. 1.25 is here, okay? And here I have 1, and here I have 0.25. In place of 2, I have just replaced 1.25. And here on the right hand side, I had 3 initially. Here I had 3.5. Is it breaking the binary search tree constraints? No, right?
No.
It's still following. So what was the trick that I did? If I would have replaced, let's say, 0.25, would it work? Let's say in case of 1.5, I would have replaced 0.25, and then I had 1. So this itself is wrong. 1 is a larger number, but it is occurring on left hand side of a smaller number. So that would have been wrong. What are we doing? Since we need to take an element from the left subtree, since left subtree is smaller, all the element of a left subtree is smaller than 2, I would try to take the largest of those elements so that it is nearest to 2. And all the element which I did not take and were the part of left subtree, those elements will follow the less than property, because I have effectively chosen the largest element from the left subtree to replace 2. Now we know that since all the element on right subtree is anyway larger than 2, so all the element of the right subtree are obviously larger than all the element of left subtree. So even the largest element of left subtree must obviously be smaller than even the smallest element of right subtree. Okay. So that's why if I choose the largest element of left subtree, then this would serve me two purposes. First purpose, all other element of left subtree are bound to be smaller than the element which I chose, and that's why all other element of my left tree after I place my new element would follow the less than condition, and all element of right subtree would anyway be greater than the largest element of left subtree, because those are right trees, so they are anyway greater than 2, right? So obviously they would be greater than any number which is lesser than 2. So that's why this satisfies both the scenarios. Okay. So if I would have taken 0.25, it would have served the right subtree part. That's not a problem. But it would have defaulted on the left subtree part. Right? This would be the error. So choose the element which is largest in left subtree to replace it with 2. Or otherwise, you can choose just the reverse of it. You can choose the element of the smallest element of the right subtree. Just the reverse, just the same logic, but the reverse application. Take the smallest element of right subtree, which is 3 in this case, to solve. Right? So if I do that, so how the tree would look? 3, 2, 1, 0.25, and 1.25, and 3.5. Fine. So you see that my condition is still holding. So either choose two options: largest element So that was regarding the deletion of element from a binary search tree. Okay, all the three cases we have discussed. When it's
Sir.
leaf node, Yeah,
Sir, here when we replace the 1.25 with 2 while deleting 2,
yeah.
then the condition of the 1.25 was the child, no, 1 was the parent. But when we replaced it, 1 became the child and 1.25 became the parent.
Yeah,
Whether this will conflict or not.
exactly. Now the thing is, what did we discuss when we started our this binary search tree topic? That it may look like you. So let me come to here. What was it? This part I told you that the second and third condition is actually good for, I mean, initial time, the first introduction to the data structure, you see these two as the condition, that is fine. But these are not actually the real conditions. These are derived because any left child would be located left hand side of parent, not because of parent child. These two are happening because left child must essentially and implicitly be located on more left in the data structure than the parent, and that's why it's a left pointer. That's why it's the left child. And right, accordingly, right should be located more right of the parent in the data structure. So because of that, left and right, the greater and the lesser value thing is happening. Nothing because of it is parent and it is child. Someone is parent, someone is child. Someone parent-child relation was happening in heap. Here, it's not parent-child relation. It may look that, okay, 4 is smallest, after that 6 and after that 7. So, both 4 so the left child must be lesser than 6 and right child must be greater than 6. Now that is correct, but that is not I mean, what should I say, theorem. Why? Because parent and child, if they change, right? If I change the parent and child, then I would follow only one rule. The one which is on left would be smaller, the one which is right would be larger. That's the only rule. So don't see it from the perspective of parent child, just see it from the perspective of which is on left and which is on right. So here 4 is on the extreme left, so it is lesser than 6. I mean, even if you compare relatively, 4 is on left side of 6, so 4 is lesser than 6. 6 is on right side of 4. 6 is right side, right? Right side. So right side of 4, and that's why it is larger than 4. If you just consider in that form, what happens to that example? That if I replace 1.25, so 1.25 becomes parent, but 1 becomes the left child, right? Now left means smaller, so 1 is smaller than 1.25. Okay, and 0.25 is further smaller than 1, so it is also towards the left. So in binary search tree, parent child thing is not a problem, left right thing is the main idea. Okay, so you see here left 1 is on left side of 1.25, right? So that's not a problem. 1 is smaller, that's why 1.25 is larger.
Okay, okay, fine.
Fine. So now insertion, deletion, and basic idea of binary search tree is done. The second point is how do we search in a binary search tree? And by the way, why do we call it search? Now we remember in heap, I would actually ask all of you to answer this question, that what was the time for searching a random element in heap. So if I give you a random element, right, in a heap, how much time do you need to search that element in worst case? So basically, since we did not have any relation between the left and right child, right, only thing that we could have done is we have to search all the element one by one. So searching a specific element in a heap, okay, searching a specific element in a heap must always take you the order and time. So that's just simple linear search, not even binary search. So it's simple linear search. The reason for that is you do not know that whether the left child is smaller or right child is smaller. There were no relation between left and right child in heap. Okay, so you have to do an order in search in order to find the random element in heap. Fine. This thing I discussed in detail why it would take order in. So just revisit the heap discussions. Now, what is the feature that I am getting in binary search tree? The thing is, binary search tree, I have a relation between the siblings. all the left elements are smaller. So if that is the case, if I take that initial tree only, okay, let's take this tree. So let's say this is a tree, okay, and in this tree I need to search a given element. Let's say the element that I want to search is uh, where is 12, right? Or let's say where is 12, or where is 15? Let's take the example 15. So I want to search, is there a 15 number in this data structure or not? So you come at 7, right? You know that left hand side element would be smaller, right would be larger than my current element. So you compare the current element with 15 and you see that 7 is smaller than 15. So that means if 15 is there in this data structure, it must be there on the right side of my current location. So you move right because it is greater than 7. 15 is greater than 7. So come at 8 and you check that how much, is 15 greater than 8 or not? And you check that, okay, 15 is still greater than 8. So I must move right. Whenever greater, move right. Whenever lesser, move left. So again, we compare with 19 and see is 15 greater than 19 or not. And you see, no, 15 is lesser than 19. And that's why I should move left. Okay. Come to 12 and compare whether 15 is greater than 12 or not. Yeah. So 15 is greater than 12. So finally you come right and meet 15 over here. So at every step you can take your decision that whether I should take the left path or whether I should take the right path depending upon what is the current value and what is the value of the node that I am going to insert. Fine, on these two things you can take this call. So at each step, essentially for a very bushy tree, very dense tree, at each and every iteration of this thing, you can actually ignore out of the two options, you can ignore one option. Right? Whether if there I can go left or I can go right. So which side I can find 15. At every step you can take the decision whether I should move left side from the current node or whether I should move right side from the current node. Fine. So that means every time you are halving the space, right? So at this level you are halving the number of iterations. Every step you tell that I don't want to go right and want to go left. So that means all the subtrees which were there on right side were ignored. So every step that you take that ignores half of the area, half of the current subtree. Okay. So you know that this is again same thing happened in binary search. Every time you were actually ignoring one half of the array. For every comparison, you could ignore one half of the array. So let's say when we were at 7, right? We directly decided since 15 is greater, I will move right. As soon as you take this call, you simply did not visit all these nodes. You simply eliminated all of them. Okay, again at 18. Now 18 has no left children, but let's say at 19. 19, as soon as you take the call, I move left, you actually eliminated all the right child right child traversal. So every call you actually half the current subtree. Fine. So that means if you are halving multiple times, that is the complexity that we get is log n, right? From your complexity understanding, you should know that. Every time if we halve it multiple times, so I would reach the end by log n iterations. Right? Simple this thing. If 2 to the power k, if I do half, right? So if I 1 by 2 to the power k, right? If that brings me to a single element, by dividing by 2 every time for k number of times, then what I can write is 1 equal to 2 to the power k, or if I accordingly go ahead, so let's say if I take log, this becomes, sorry, not 1 n. If I have n elements and I divide it by 2 to the power k every time, so my log n base 2 on left hand side and it would be k log 2 is 2. This is 1. So you get k is log n. same proof that basically you can divide it by log n times, or you can reach the leaf node by log n iterations. Fine. So that's why any element that you can search in a binary search tree, that would take you order log n time. In heap, it took order n time. Right? And like in binary, any sorted sequence, in binary search also you did the same. Okay. So searching time in binary search tree is order of log n. Searching time in heap is order of n. So searching, deletion, insertion, all these things are done. If you go to the code, these are very simple code. So how can you do the search? Just take a pointer from start from the root node. Okay, just write if, let's say this is my current value is depicted by node dot data. If that is lesser than your key value which you want to insert, you just, so key is greater, right? So if key is more, I must move right hand side. So you simply recursively call insert, sorry, not insert, I mean search. Search on which side? Node's right side. Okay. Else if, if you check if node dot data is greater than key, then key is lesser and I must search on the left side. Fine. And let's say if it is equal to the, let's say here again you had, if my node data is equal to key, then you simply return, return whatever position or whatever you want to return, the data, or return yes it has been found, something like that, whatever. Fine. So that's the idea. If also you can have it as the base case, right, till it becomes null. So simple code, simply recur all in binary search tree, insertion, deletion, whatever you do, that would be a simple binary search tree. That would be a simple recursive code. So we also saw the traversal, right? The in order, pre-order, they were also simple recursive code. That's it. So yeah, only the deletion, this part, right? This two children deletion, that is a bit difficult, but I think if you have understood the concept, so that is still easy. Right, so if you, what would be the condition for that? If your node dot left is not equal to none and node dot right not equal to none, so that means both of them have some subtree on left and right child, right? In the case of T. So what do? You simply replace node with the greatest of this element. So either, so let's not write node, let's say one T variable is there, in that you put the node which is the either the greatest of left subtree or the smallest of right subtree. So as of now, consider I am proceeding with the greatest of left subtree. So I would find, let's say max is a function which finds the maximum element, and in the max you pass node dot left. So maximum element from the left subtree could find, okay, and just by returning that into T, and you can then swap T and your 2. Not swap, replace your this current node with the value T. Just do that. So these codes would be very easy to understand once you understand the process. They are simple recursive code. Fine. So insertion, deletion, search, all those things, and basic property of binary search tree we did. Also traversal we saw, what are in order, pre-order, and that in order, pre-order, and post-order traversal. We also saw the significance and how in order traversal always prints the sorted array. Fine. Okay, so I am moving a bit fast because there are a lot of things to cover, so that's why. So any doubt till now, even if you have some, even if you do not understand most of the thing, just rewatch the discussion here and the lectures. I hope it would be clear. But yeah, any general doubt?
No, sir.
Fine. So now we would see the problem of having a binary search tree. We know the problem of heap. Heap was very efficient to give us the minimum element or maximum element in a log n time. Okay, and it was quite easy. It was dynamic. That whatever, if I add an element, that also took log n time. So array could have also given you a order one time element, right? In the smallest or the largest element in order one time. But as soon as you insert an element in a sorted array, it would take you order n time actually to insert the element at the proper position. Even if you search using binary search to insert an element at the correct position in a sorted array, but still in order to insert that element, you have to shift all the elements one position, right? So that's why in order to shift all the element by one position left or right, that would take you order n time. So array could have given you minimum element in order one time because the first element would be the minimum one. But since insertion into an array is order n time, so any real life problem where we do insertion as well as finding the minimum. Now please pay attention over here. Whenever in a real life problem or in an algorithmic problem, whenever we do two operations very frequently, operation number one is getting the minimum out, and operation number two is adding more nodes into the data structure in which we are operating. So insertion operation and extract bin operation, if these two operations happen very frequently in a real life problem, then arrays, sorted arrays might not be a good choice, and other data structures are also not good choice except heap. Why? Because sorted array although gave you order one time minimum element, but insertion in a sorted array would take order n time. But heap, it would not give you order one time element, it would take log n time to supply you the element, the minimum element, but it again takes order log n time only to insert. So both insert and search takes, both insert and extract bin takes order log n time in case of heap. So that was the advantage of heap, and that's why we use Dijkstra and Prince with heap, and I will discuss that in the next session again. Because Dijkstra and Prince, both of them were finding the minimum element, and both of them were adding more nodes into the, every time we are finding a new edge, we are considering that for the minimum, right? So that means you are constantly changing the data structure on which you are working with the process, with the proceeding of the algorithm. So since in this kind of two algorithm, we are inserting as well as we are finding minimum multiple times, that's why heap is a better choice over there, because it provides you both the operation in log n time. That's the whole idea. Now the problem with heap was searching. Extraction, insertion, log n is fine, but whenever we need to search an element, then we are in a trouble. So we had to do order n time search. That was the problem. And that's why we came for binary search tree, where we can do order log n time search. So that's the crux of the summary of all these things, that order log n time search can be facilitated in a binary search tree. And finding minimum, how much time it would take to find the minimum element in a binary search tree? In heap, finding minimum, if your minimum finding, okay, was log n. In binary search tree, how much time it would take? See, we know in a binary search tree, the leftmost element is bound to be the smallest element. Okay, so all you have to do is traverse left until you reach none. As soon as you reach none, you know that I have reached the leaf node and print that node. So you just have to travel left in a recursion. And the base case would be if any node equal to none, okay, then you simply print the data at that point. The data of the previous node. That's it. Or you can write it like this. So let's say you have a while loop in that you proceed while nodes next or nodes left is not equal to none. Why I am writing nodes left? Because when you would be at 1, right? So node would be 1 and left of node would be none, right? So if I write node arrow left not equal to none, that means only the position where it would actually fail is this position, right? Because node, when 1 is the node left is none. So at this position, it while loop would terminate and you would come out. So as soon as you come out over here, let's say the while loop terminates over here. So then you can directly insert at this, you can do your work at this position, because now you have reached the proper position. So you can simply print that node is the smallest element, because now I have reached the leftmost element. So simple codes, all the binary search tree codes are quite simple, you would understand. oh, sorry, I did not discuss the running time, which was the main idea. The idea is to, so basically you're traveling left till you reach none. So that is essentially the height of the tree, right? Whatever is the height. Now the problem is, if you are searching an element or finding the minimum element and you have to travel the whole, this height. So the finding minimum in binary search tree essentially should take you log n time only, because height of a binary tree is log n. Provided there are n nodes and the tree is mostly balanced, the height of a binary search tree is log n. But what happens, I discussed that a binary search tree can be like this as well, right? Directly, linear kind. Right? We discussed that. So this kind of binary search tree is what we call skew binary search tree, because it is skewed in one direction. But it is still a binary search tree because it does not violate any condition. So in this kind of tree example where the tree is a skew one, right? So this is essentially just like a linear data structure. So if there are n nodes in this linear data structure, so all n would be on left hand side only. I would not have that feature of going to one side by neglecting the other half. So if I would have a node on right hand side, so when I am at this position, I could take a call depending upon my key value and this node's value, whether I should move left or whether I should move right. So depending upon that call, I would ignore all the other elements on the, let's say, right tree and move towards left. But this feature I am not getting when I have all the nodes lined up in one side. Okay, so this is essentially a skew tree, or in this scenario, if I have n nodes, so I would not get a log n height because all of them are in one side only. I would get a log n height when around half of them would be on the other side as well. So these nodes are utilized on the right side. But if I do not utilize any node on the right side, all of them would fall on left side. And in that case, this would work like a linear data structure. And in that case, ideally the worst case is, so this is the theta case. Most of the time it would be log n. But ideally the worst case scenario of binary search tree is order of n. So we had this idea of log n, searching and insertion, finding the minimum element, all those things were working in log n for binary search tree. That was quite good. But only problem is if it becomes skew, if it becomes lined up in one direction, then all of this problem would give me order n time, right? Which is not desirable. So in order to eliminate this problem so that the tree does not become skew on one side, we have to do something what we call balancing the tree. So as soon as we see that the tree is getting skewed in one side, we would balance the tree to have equal weight on both the sides. Okay, so that's the whole idea of balancing. And same binary search tree, the same binary search tree which got disbalanced actually, which ran into this skew property, right? If we do the balancing, then it would become like a tree which has both sides, right? Like this kind of tree which has both left and right subtree. And in those trees, again, I can guarantee, since now my half of the nodes are on one side and other half on other side, at each level I am doing this, so my height would be log n. So again, my extract min, my searching, my all the thing would boil down to log n type complexity, because at most I have to travel through the height. So everything would be order of h, and order of h would be order of log n. So only thing is, I have to make sure that I do not make my tree into a skew tree. All the time my tree should be, if not completely, I would try to keep it as balanced as possible, so that I can get the benefit of having a log n height, and that would fetch me the benefit of searching in log n as well as finding the minimum element in log n time. Okay, so that's the whole idea. Any doubt?
Which one is a skewed BST?
This one, if I just have like this one side. So I took that example now. So let's say I have 10, 9, 8, 7, 6. So this is a skewed binary search tree. Because what is the property of binary search tree? Every node must have, since it is a binary tree, BEST. Since it is a binary tree, that means all nodes must have lesser than equal to 2 children. Since it is a search tree, that means the left child must be smaller than the right child. Okay. So if these are the property of a binary search tree, let's apply that over here. You see, all nodes should be all nodes should have less than equal to 2 children. So 0, 1 or 2 children each node can have. This node has 1 children, this node has 1 children, all of them has 1 children, only this node has 0 children. So valid. Also I know that left child should be smaller than right child. So 10 is the root node, so fine. 9 is left child, but there are no right child of 10. So arbitrarily 9 satisfies. Accordingly, arbitrarily 8, 7 and 6 also satisfies. Fine. So this is a binary search tree. That's why. That's why I'm calling it as a binary search tree. So when it is a binary search tree, that's the problem I discussed. If it is not balanced, if it is skewed in one side, then I cannot use the fact that I can ignore half of the element because they are larger than somewhere or smaller than somewhere. So that feature I lose, and if I lose that feature, I mean, all the numbers which I had, they would arrange in only in one side. That's how it would become skewed. And if it becomes that, then all n numbers would be on one side, and therefore my order of height would be actually order of n. But if I have a balanced tree, so then my order of height itself, both the thing, order of height would become order n in case of skewed tree, order of height would become order of log n in case of a balanced tree. And since all of my algorithm works on the height, so everything would be order of log.
Okay. Got it. Thank you.
Now the thing is, the main challenge is that I have to keep the tree balanced. Otherwise, I am running into order n time. If it is not balanced, if it is not having these branchings, right, both left and right branching, then I would run into a tree like this, and that would give me order n time. If I keep it balanced, it gives me order log n time. Log n time searching, log n time inserting, log n time finding the minimum element, all operations log n time. Fine. So now we have to somehow think about balancing or keeping the tree balanced, having this branch structure. That notion or that problem is actually solved by what we call the AVL tree. Okay. AVL tree is what? This is nothing but a binary search tree plus balancing. Okay. So all AVL tree are basically balanced binary search tree. So all the property of binary search tree would be there. Only thing is they would also be balanced. That is, they would never become skewed. Right? So now what we would learn that what is an AVL tree and how it looks like and how it works. This is very important and also a bit difficult for initially at least. Once you see the thing, once you go into practice, it would become easy. So I would ask all of you to please pay attention over there and ask doubt at each and every step whenever you feel there is a doubt. Okay. So yeah, give me a minute. I would resume back in 1 minute. Okay, fine. So let's continue. So we would see avial tree just by performing insertions into a binary search tree. So we have learned what is an avial tree. Avial tree is just a binary search tree with balancing. But we don't know how we do the balancing. We know by doing balancing, we would ensure that the tree does not become skewed, right? But we don't know how we do the balancing. So let's take an example and create an binary search tree. And in the process of creating the tree, we would see that it is getting unbalanced. It is getting skewed. That is that linear kind of structure, right? We saw could become something like this or something like this in one direction, either left side or right side. So we would see how we can deal with that, and then we would go to the codes also. Yeah. So if I take a small example at first, let's say we have to make a tree with the numbers 1, 2, 3, 5, 6, 7, 8. Fine, these are the numbers with which I have to make a tree. Okay, so let's do that. A binary search tree, Now avial tree is just like binary search tree plus the balance. So just keep in your mind binary search tree. So now on binary search tree, how do we do the insertion? At first, 1 is itself, so 1 is there. Right? Then we got 2, so we have to insert 2. Now 2 is larger than 1, so 2 would be inserted on the right side, right? Fine. Then 3 is there, so I come over here at 1 and I see 3 is larger than 1, so I would move left, I would move right, and I would come to 2 and see, okay, 2 is again smaller than 3, so I would again move right, and I see right side there are no elements, so I insert 3. Right? Now you see, just by inserting in this sequence, I am getting this Q kind of structure. If I go one more step, it would be 4 like this. So the definition of balancing comes into play, and how it works is, so let's keep it till 2. Balancing means the avial tree constraint. So this is the avial tree property now, avial tree property. This says that if I have a node like this and I have a tree, so let's consider there are some nodes on the left hand side, let's call it T1, and I have another subtree on the right hand side, right? Let's say call it T2. So this triangle means trees, so this basically means I have many nodes. I can have a structure like this, right? All of them together, I'm writing it as one, this triangle kind of thing. So that means there are many nodes in T1 and many nodes in T2. And this is the node under consideration, current situation. So avial tree property says, I would consider this whole tree as an avial tree when the left child height, right, the height on the left side minus the height on the right side, right, the height on the left side minus the height on the right side is no more than 1. When I say no more than 1, it can happen that left side is deeper and right side is shallow, right? So something like this. So let's say this is a binary tree. If I consider this node as my point of considering, the node under consideration, so what is the height of its left subtree? Left subtree is this one, right? What is the height of this left subtree? This is the node under consideration, the root node. So what is height? 1, 2, 3, 4, 5. Height is nothing but the maximum number of edges that you can find till any of the leaf, right? So these are also leaf. These are also leaf, but here the number of edges are 2, and in this case the number of edges are 1, 2, and 3. But the definition of height is, maximum height is, you have to go till till any leaf which is located farthest away from the node under consideration or your root node. So that's why this leaf is located farthest, and that is the height actually. 1, 2, 3, 4, 5. So 5 is the height on left side. Right side height is 1. Also I could have gone 2, but I can have a leaf node which is farther. So 1, 2, and 3. So this leaf node is much farther. So max height is 3. Here max height is 5. The avial tree property says let's come back over here. The ABL tree property says that 5 minus 3 must be less than equal to 1. Now, here the thing is 5 minus 3 modulus. Because in this case 5 is, I mean, I am doing left minus right, right? Left, height of left minus height of right. But what happens if I just make the mirror image of this tree, right? There is a lateral inversion. So in that case, my left subtree would be height 3 and right subtree would be height 5, right? So something like this I mean. Sorry, not 3. Yeah, this node is there. So yeah. And accordingly, just copy this in this place, this subtree. Fine. In this place actually. So this would be a height 5 subtree. Okay. So in this case, what would happen? 1, 2, and 3 is the left side height, and 5 is the right side height. So I always do left minus right. So 3 minus 5 would be minus 2. Okay, and here it would be 2 actually. This would be 2, and here it would be minus 2. So whether it is minus or not, that doesn't matter. That is happening because either the left side is skew or the right side is skew. I mean, sorry, not skew. I mean the height is more. Fine. So I don't worry about the which side is more in height. I only worry about even if any one of the side is greater in height than 1, I can allow a difference in height of maximum 1. Fine. So that means what? If I have put a modulus, if you just actually write it, I can allow a difference in height of 1 or minus 1. Fine. So if there is a difference in height of at most 1 or minus 1, then I can still allow and tell that okay, this is a balanced tree. But if the height difference grows more than 1, then I would not consider it as a balanced tree. I would call it as a partially skewed tree. And a completely skewed tree is the one example that I discussed, something like this. So even a balance factor, I mean even a difference in height of more than 1 in the tree, we assume it to be unbalanced and we would do the needful to balance it. Right? So you understood what are the constraints of an ABL tree. ABL tree is a binary search tree only with an extra property that difference in height of left subtree minus the right subtree should not be greater than 1. Modulus, I mean modulus should not be greater than modulo should not be greater than 1. Fine. So and by doing this, you can guarantee that I would not become skew. Why? Because you just consider a skew graph. You see what would be the height difference? So if you consider the root node, there are no elements on right side. All elements are on left side. So the height difference is basically your n. Actually n minus 1 because n minus 1 edges are there. So that becomes your order n. And that's why because of this order n, your all algorithms are running slow. Right? So that's why now we would do the balancing by following the rule that I would at every step of the tree, when as soon as I insert, right? Now when the height would increase? The height would increase when I insert an element. So after that I insert, let's say 3. So 3 is inserted here. So obviously the height is increased by 1, right? Due to this extra node that we had to connect 3. So every insertion actually makes a change in the height, and all accordingly every deletion also makes a change in the height. So whenever we insert or delete an element in a binary search tree, we have to take care of the balancing. Fine. Now, just a second. Now with that logic in our mind, we would now do the insertion. So every iteration, every insertion or every deletion is a prospective operation to increase or decrease the size. I mean, make a change in the balanced situation. So that's why every insert or delete, we would, after inserting and after deleting, we would check that whether the height condition is valid or not. That is, for every node, we would check for every node, right? We would check for every node whether the left subtree height minus the right subtree height for that node is within modulus 1 value or not. Okay, for every node we would do that. So now let's do the insertion and let's see how the balancing actually happens. Now this is the main part. Please pay your attention here. If you understand all this example, everything, not this example, after this one more example I will take. These two example, if you understand, then it would be fine. So 1 and 2. So first insertion, 2 is my first insertion, right? So I would check whether the height is okay or not. So check height of 2. There is no left subtree, there is no right subtree. Okay, so both left and right is 0 and 0 minus 0. We told that we would do the left minus right height. That's the property. So left minus height is 0 minus 0 is 0. So here the balance factor. So this left minus right height, we call it balance factor. Okay, let me make it bigger. So balance factor, which is 0. And here the balance factor would be, for every node we calculate, right? Left subtree, there are no nodes. Right subtree, I have one node, right of 1, right? I have one node. So, and it is connected by one edge. So height is 1. So left subtree height is 0, right subtree height is 1. So 0 minus 1, which is equal to minus 1. Now minus 1 and 1 is fine, right? There is no problem with minus 1 and 1. And that's why we would actually consider it as a balanced tree as of now. Is my presentation visible? Some of you are writing that it's not visible.
Visible.
Visible, it is visible, sir.
Okay. Fine. So here the balance factor is 1 and you remember ABL tree condition that it should be your, let's say I call it the left height minus right height. Modulus value must be less than equal to. Fine. That's the condition for being balanced. For being balanced.
For each and every node.
For each and every node. For each and so that's why I write, right? I inserted 2, but after inserting 2, I check that 2's balance factor is 0, and then I also check 1's balance factor is minus 1. So both all the nodes we would check after every insertion.
Hmm.
Right. So now let's proceed further. This was 2. Okay, now the next number is 3. So insert 3 over here. And again calculate the balance factor. So left and right 0, right? Node nothing. Left there are no nodes, right only 3 is there. So 0 minus what? 1, right? Height is 1 on the right. Right subtree of 2, height is 1. So 0 minus height 1 is equal to minus 1. Balance factor is 1. How many nodes are there on the left side? So what is the height of the left subtree of 1? 1 has no left subtree, so the height is 0. And what is the height of right subtree of 1? 2, right?
2.
So 0 minus 2 is minus 2. Now this is a problem. So see, we could allow up to minus 1 and 1, 0. Minus 1, 0 and 1. These three numbers are allowed in height. But minus 2 or 2 is not allowed, or more than that. So that is an indication of getting a more skewer version of your trees, and that you can see physically also, that your tree, visually also, that your tree is becoming skewed. So now we would do balancing. Now the main thing comes, how to do the balance. There are, in order to balance, what we would do is we would use rotations of the tree. Right? We would rotate the tree either on left direction or in the right direction. Okay. Now, how to decide whether I would rotate on the left direction or the right direction, and what do we mean by rotate? I would come to that. Rotate means, like you see that this tree visually, just now see this thing visually, then I would come to the theoretical part, how to identify which side to rotate. But visually you see that it is becoming skewed towards the right hand side. So can I rotate it something like this towards the opposite direction and get the result like this? See what I did. I just held it from this point and rotated it in this direction. Right? So if I rotate, so 2 would come over here, 1 would go down, and 3 would come over here. So that means you are rotating, right? Just assume that you are rotating by holding 2. So 2 comes on like this, 1 goes left and 3 goes right. Is that intuitive? Is that okay? Visually at least I am asking. Any
Yes,
doubt
sir.
in, right? So since this was on the rotate, I mean, since this was getting a line kind of thing rotate, I mean, skewed towards right, right? That's why rotated towards left. So this is what
We
we
are
call a,
we are
yeah.
selecting 2 because it is at height 1. Is that why we are selecting 2 to rotate?
I would come to that. Huh? I would just come
Okay.
to that. Huh? So basically, yeah, we are doing that, but actually the thing is we are selecting 2 means this is not selecting. I told you just to understand it visually. We are rotating on one only. Right? We are rotating itself on one. So if I move one right side, I mean towards the left hand side, what would happen?
Okay.
Same thing, right? You're just holding one and pulling it down, pulling it right, clockwise, anti-clockwise direction. So one would come down and 2 would be at the top and 3 would be on the right hand side. So, but I would come to on which is the node, I mean, on which you would apply the rotation. Those things are different. I would come to that. But now you see, now if I calculate the balance, this would be 0, this would be 0, this would again be 0. So all 3 of them are 0 now. Right? So this is my balancing. I made a rotation. What rotation did I make? A left rotation. Why? Because in this direction I rotated, right? In this direction. That's a left rotation. Okay, now let's insert another number on this tree. So now 3 is there, so 4. 4 would come here, right? 4 is larger element, so just like binary search tree, you go right to insert the larger one. So 4 you put over here, and now you see 4's balance is 0, 3's balance is no longer 0, it would become what? -1. 2's balance again would no longer be 0, it would become what? 1. Here the height is 1, here height is 2. Right? So 1 minus 2 is -1, and here the height is 0. Now you see 0 minus 1 minus 1 0. So this is a valid balanced
Yeah,
tree.
still it is valid.
Correct. Now I would insert 5. Next element. Now see, this is 0. This would be -1. What would this be? What is the height
It will
of
be
3 now?
1. It will be 1
Why it would be 1?
because it has 0 on the other side and
Minus 2, minus 2,
minus
2.
minus 2.
Minus
Sorry.
2, minus 2, 0 minus 2.
Exactly. So it should be -2 because this is 1 edge, 2 edge, right? Height is 2. So now we see again one problem happened and we ran into -2. And obviously, if you see on the top, this would become what? 1 here and 1, 2, 3 here.
Minus 2, minus 2.
This would again become -2. And this is still 0. So we have now 2 nodes which are in -2 position. The idea is the node that you inserted, right, at the end, you would start from that and find the first position where your balance condition is getting altered. So you would not come from top, you would not come from root, you would come from bottom to the position where your, the first occurrence of your balance condition, the first occurrence of failure of your balance condition happens. So I would consider this 3 node as my area of work, not 2. I would work on 3. Why it is so? Intuitively, if you see this -2 is happening because my right hand side tree is becoming a more skewed kind of tree. If I can sort out this right hand side tree and reduce the height somehow by balancing, then anyways when I do the calculation for 2, right, the height of right hand side, if it decreases, then anyway my negative value would decrease. So the factor for 2, the balance factor would for the element 2 would improve. The balance factor for element 2 would improve if I can somehow improve the balance factor of 3. Because anyway, this is the right tree for 2. So if I can improve this right tree, anyway 2 would be improved. So that's the intuition behind the idea that we always start the work from a point which is more closer to the newly inserted node. That is from bottom to top. From bottom to you are moving like this. The first point you get, that is your point of work. So I would work at 3 now, right? Now again visually you see it is kind of a right side skewed kind of thing, right? So if I again move it towards left, just like the previous idea, So then it can fetch me some good result. So let us do that. How it would, I would take 3 and snatch it down. So what would happen if I snatch it down? 4 would come here, 3 comes down, and 5 remains in its position. Now again we check the balance. This is 0, this is 0, this is 0. This is what? 1 is the height on this side and 2 is the height on right side. So 1 minus 2 is minus 2. So you see automatically 2's height got improved. So there is a balance tree now. Okay. So accordingly, if you just proceed accordingly, you would see if I add 6 here, then what happens? Tell me the balance factor quickly for all the elements. 6 is 0, 5 is 0 minus 1 is minus 1, and then 4 is 1 minus 2 is minus 1.
It'll be minus 2. 2 will become minus 2.
So 2 becomes minus 2. I told you we always move from bottom to top wherever I get the first point of fault rate, right? Fault. So 0 minus 1 minus 1, 2. So this is our point of work now. Now what to do? Again same thing. You see that it is getting towards the right hand side skew kind of thing. The skewness is on right side, right? It's moving right. More elements are there on right. So same intuition, rotate it left. So if I hold 2 and bring it down, what would come? The next element would come at top, 2 would go down, 1 would go further down, right? And again the elements would be like this. Now the $1 million question is, this is fine. This is like a chain. So this part is working like a chain. This part. I just pulling it down like this in the bottom way. But what happens to 3 now? 4's left child was 3. Now 4 has become the root, right? So where should I place 3 now?
Right of 2.
Correct. Because at the end of the day, this is a binary search tree. So you should always place elements so that this solve. So that when you look from top, it should follow the sorted order. Okay. So 1, 2, 3. So you move 3 over here. So this kind of a little bit of tricky handling you might have to do, okay, while making the rotations. Rotations are quite visually acceptable or intuitive, but sometimes it may become a little difficult, and this kind of small changes you have to do.
So
now
this,
again,
can you explain the placing of 3 again? It's
Yeah,
clear
correct.
up to.
Correct. So if you see this part, I am just pulling it down, right? So when
Right.
I pull it down, so 1 comes further down, 2 comes down, and 4 becomes the root because 4 comes here, right? As soon as 4 becomes the root, I have to make 2 as the left child of 4, right? Because this is the chain. This is the chain kind of thing. So if I pull it down, so 2 would become the left child of 4. So 2 would come here, 4 would go like this. So if I make 2 as the left child, right? So then I lose the 3. 3 was the left child of 4 initially because 4 was not a root. So that's why it held 3 as its left child. So, but now my graph has become something like this before 3. Assuming this is a chain, this has become something like this. So where to place 3? Now we know ABL tree is a binary search tree. So what the thing is, everything should be there in a sorted sequence when I look from top.
Okay.
When I look from here.
Clear.
Right?
Yeah.
That's
Yeah.
the whole idea. And the main idea again is the left side should be smaller, the same property of BST. And so if I have to place 3, 3 is what? Larger than 2 and smaller than 4. So if 3 is larger than 2, it should be on right side of 2.
Right.
And if it is smaller than 4, it should be on left side of 4. So it is already there.
Right.
I told you, right?
Yeah, it
The
remains.
element which
Yeah.
is on left of.
Right.
Yeah.
Thank you.
So that's why. Okay. Now we would proceed one more step, and then I would stop this example and take a more complex example.
Sir, why can't we put here 3 in between 2 and 4?
Where?
Why can't we put 3 in between 2 and 4? In between?
There only we have put, right? Where you want? Here.
Yeah, why not?
Okay, let's see what happens if we do something like that. Four was
Okay,
there?
got it. Okay, got it. Again, it will be,
Exactly.
yeah, got it. Again, the same problem.
Same problem. The
Got it.
height
Got it,
problem.
got it. Got it. Thank you, got it.
Fine. So this is our graph. Now let's see the balance factor. This is 0. This is 1 minus 0 minus 1 is minus 1. This is 2 minus 2 is 0. 0. 0. So again it is a balanced tree now. And okay, so let's do one more step. Would there be something significant happening? If I add 7 here and I pull 4 down and 5 goes up, no, nothing much significant. So yeah, same thing would happen. So you can just repeat that. So 7, 8, so whatever, the thing is every insertion we do and after that we check the balance factor. We go from bottom to top. In our path from bottom to top, wherever we find the balance factor to be altered, we would actually rotate depending upon left rotation or right rotation. So if I would have taken an example of the other order 8, 7, 6, 5, 4, 3, 2, 1. In this order 8 would be like this, 7 would be like this, 6 would be like this, and this would be the first time my balance factor would be lost. So I would convert this to a which kind of rotation. Now it is skewed towards left, so I would rotate towards right. So my 7 comes here, 8 comes here, and 6 comes here. So that would be your right rotation. Right? This was your left rotation. And accordingly, the same steps, just the laterally rotated one.
Same
Same
step.
thing. Now, the question is, let's take another example and we would see an interesting pattern happening. Till now, we saw that the skewness was happening only in one direction. So what do I mean by that? So let's say I had either this kind of thing. Okay, maybe if I had one or two nodes here, but still the maximum weight was happening in one. That is, if this is happening on left side, right? Or if I have a structure like this, so I see that the skewness is happening on the right side. Fine. Now, if I see that structure something like this, okay. So, can you tell me what is the let's draw the number such that it. Just a second. This is 0. This is 1 minus. Sorry, it's minus 1. This will be 2 minus 0. So this will be right. Okay, fine. So let's take a number so that it satisfies this things. So let me take it as 20. Less than 20 is, let's say this. And let's say so suppose I have a tree like this. Okay. Now let us see the balance factor. This is 0 and 12 was the yeah, 12 was the last element that I inserted. So 0. Here the factor is what? Minus 1. Here the factor is what? What is the balance factor of 15?
2.
2, right? And this is 3 minus 1, which is 2 again, and this is 0. Now we can see that this is kind of that left thing happening. It's more skewed towards left. But if it is skewed toward left, I would do the same kind of logic. I would try to move it toward right. So let's do that, see what happens. So I pick 15, 25, 10, and let's say after this we have 12 over here. Right? So this becomes still a balanced, I mean, there is no problem with it. Is there a problem? No, right?
No, yeah.
No problem. So in this question, let's say I add another one element over here, which is, let's say, 13. Fine. And here on right hand side, let's say I add an element, let's say 16. So 16. Okay. Now let's see what are the factors in this stage. Okay. 16 was balanced. Yeah, this was 2, this was 3, so no problem. Yeah, 13. This is 0. 12 is 0 minus 1 is minus 1. Now this is imbalanced, right? So let's say 13 was the last element that I inserted, and by inserting 13, I have made this imbalanced. So this is becoming minus 2.
Minus 2.
Okay. So I'm not going for 15 because this is our first point of work, so I would do over here. So what to do now? Can you tell?
Right rotation.
10, 12. Again, it is becoming balanced, right? Any problem?
Means we can rotate at any point.
No, yeah, you can rotate. You are doing that only, right? For 3 element only you did.
Now, what is the general principle to rotate? Where to rotate?
No. So let's get back. Let's see what happened initially. So 15 was there, 12 was there. I am not taking that kind of example yet. So general principle is on that node only. But it doesn't matter. Why? Because let's say, how was the structure? I rotated 10 was there, right? So then I had 12 and then I had 13. It was something like this. Okay. Now, where is the first point of your
Failure.
default 10, right?
Failure.
Failure is 10, right?
10.
So this is the point where you would rotate. Okay. So this is the point because here there is no problem. Here you would rotate. You would take 10 and pull it down.
It is general principle where it first time fails from bottom to top, going from bottom to top.
Yeah.
Then we will work on that point, right?
Exactly.
Yeah.
Okay.
And second step, where to rotate?
Second step means only so after rotating you would check that whether the balance conditions are satisfied or not. So you check here, if I rotate, it would become 12, it would become 10, and this would become 13. And you would check 20, and then it would become 16, this would become 25. Now you again check for all the elements whether the balance factor is 0 or not.
Yeah.
After rotation, you have to check whether it is okay or not. You see that balance factor is okay in all of this. These are perfectly balanced.
Again we have to check all the nodes.
I mean, see, for understanding, you have to check, but the thing is, actually, if you, by principle, by theorem, we know if you do the balancing like this, then it works. So in code, you do not have to check it. In code, you only check after inserting. So you inserted a node in a binary search tree. After that insertion, you check the balance factor, and then you do the rotation accordingly. Fine.
Okay.
But there in code you do not have to check. But here understanding, in order to confirm that the rotation actually works, I am checking that it's you see that after the rotation this -2 is gone. That's the idea. In code you need not do that. In code once you do the rotation, it works.
Can we predict the rotation? One rotation can affect up to which point? Suppose the tree is up to 100. And in both the sides, then can we predict up to which point it will affect?
Yeah. So that's the thing, that once you rotate it, so I have not yet discussed all kind of rotation. So what we have been discussing till now is only left rotate or right rotate. Right now, after this, I would take one example where you would see you would need both kind of rotation to solve the problem. Now you are asking is up to which level the problem might be solved. The thing is, whenever you see from what you move from bottom to top, right, and find the first point of faultness.
Yeah.
So when you do that, this is your point of faultness. And depending upon a specific condition, up till now we have been discussing the rotation just by visually seeing which side is skewed and I am rotating on the other side. But at this point, just after completing this example, now I would formalize it. Now I would tell that what is the factor on which you would, computer cannot see visually, right? Whether it has to do left or right rotate. So what is the factor on which you would write the code in order to do left or right rotation? When I discuss that, then you would get that once I apply on that basis of on the basis of that factor, I apply a rotation, the whole tree would be correct. You do not have to worry about that it would only be correct up to this point. It would only be balanced up to this point. It would be balanced over and all. Okay, once you do the rotations formally in the manner I would discuss now, you can be sure that those rotations would affect the whole tree and the whole tree would become balanced.
Okay.
So now your visual idea is over. Now let us do some formal thing, and before that formal thing, actually I would take this example, quite a big example, and then we would formalize it. So up till now we have seen only by making either left rotation or by making only right rotation, our problems were solved. But now we would see an example where only by making one rotation, that is either left rotation or right rotation, our problems would not get solved. I mean, the balance factor would not get back to 0 or -1 or 1 by making one rotation. Okay, so that we have to check. So I would be a little bit quick now. See what happens. 22 is the first element. After that, I insert 29 on right side because 29 is greater. 16 is smaller, so insert 16 on left side. 10 is even smaller, so insert 10 on left side. After each of this insertion, I am checking the balance factor. I just did these things fast because the balance factor would not get affected up till this point. So even up to 10, you check. What is the balance factor of 10 is 0. Here it is 1. Here it is 2 minus 1 is 1. Here it is 0. Right? So now we would go for the next step, which is delete. Okay. After 10, I have 86. So 86 is also not a problem. You see, balance factor still remains 5. Now I insert 2 on the left side of 10. Fine. Now I insert 2 on the left hand side of 10. And you see, I run into a problem at which node? At 2 it is fine, at 10 it is fine, at 16 I have height 2 right on left subtree and height 0 on right subtree. So the balance factor at 16 is 2. So that is my first point of concern, and I would rotate it, but it is skewed towards the left side. So just like our previous example, I would rotate it like this. 10, 16, 2. So this happened with one rotation. You can check the balance factor, it is fine for all the nodes. No problem over here. Okay. I will maintain all of this because after this we would need each of these rotations. We would name all of this rotation and formalize. Fine. Next thing. So after 86, what's the next element? 2 I have inserted. 19 is the next element. So where would I insert 19 now? 19 is smaller than 22, so go left. 19 is larger than 10, so go right. And 19 is larger than 16 also, so again I insert 19 over there. Fine. Again see balance factor, 19 is fine, 16 is fine, 10 is also fine. 22 has 3 here and 2 over there. So 3 minus 2 is 1, so 22 is also fine. So this is again a balanced tree. No problem. Now 17. 17, where would I insert? 22 I come, 17 is lesser than that, go left. 10 is lesser than 17, so go right. 16 is lesser than 17, so go left. Go right. And 19 is larger than 17, so go left. So 17 is inserted. Now I would again check balance. This is 0, this is 1, this is problematic. Now here I got what? Here the left hand side was what? 0, and here it is 2, so minus 2. Okay. Now I need a rotation. Now this is my question. Which side is it skewed? If you just see this 16, 19 and 17. Which side is it skewed?
Still right only.
Okay, fine. So it looks right, so then that's the problem. So this example and this kind of example would land you in trouble, might land you in trouble. This looks like right rotation because you see that, 16's right component, right subtree is the one making trouble. But you remember in previous examples, we had the skewness like this.
Right.
That everything was in one direction. Here the change happened that I got 17 pointed in the other way. So 17 is again coming towards 16. It is trying to move towards the other way, right? So I am not getting a perfect skewness. Okay, so if you just apply the normal intuitive idea that okay, the right subtree of 16 is making the unbalanced thing, so let's make it move towards left. Let's see what happens. If I move it left, I would bring 16 down, right? That's your left rotation. 19, 16. Is this a BST? Just this part.
No,
Can I say this? No, right?
Yeah.
Because 17 is a smaller number and it is located on right hand side of 19. So that's not allowed. 19 is a larger number. So any number which is
We
right.
can put
Yeah.
we can put 17 right of 16.
We can put 17 right of 16. Great. If we do that, what happens?
Here.
Fine. Then what's the balance factor of 19 now?
Okay, again it is a problem. No.
So the thing is, the solution is
exchange 16 with 17.
Exchange 16 with 17, but that is something we are doing arbitrarily, right? It is not a proper way. We would do that only, but not exchange. We would only consider rotations because the only tool we have is left or right rotate. We have to be uniform with that. Either you can use left or right rotation. So I would use left and right rotation both in this scenario. How to identify this thing, right? How to identify a situation like this? Visually, I am saying that it does not look like, but how to identify? So let us at first revisit what kind of rotation we did earlier. You remember all the rotations that we did in the previous example. Now I will formalize it. Here, right? You see, here I did a left rotation first time. Right? Which was the node that was inserted? 3 was the node. And which was the node which got the disturbance first time? 1. So you point the node, you are anyway finding the node which is getting into the unbalanced thing, right? So that is your 1 in this case. Once you get that, check whether your newly inserted node, just check in which direction is it from the first node which got unbalanced, I mean. So the node which is getting unbalanced in this example is 1.
Pardon? What did you tell?
Bear with me. I would tell what it means. When I do it, it would be more understandable. So at first you come to the node where you find the unbalance factor is happening, right? That bottommost node. That thing is I have discussed. After coming to that node, you check in which path, either left or right, I have to move in order to reach the newly inserted node. So in this example, I have to move right once because this is the right edge of 1, right side. And then again I have to move right one more time. Right? 2 times, only 2 times you have to see. If I would have, let's say if I had 3 like this, right? If I would have, assume not 3, let's say if I had a number like this and this was the newly inserted node. Okay, just assume that this was the newly inserted node. And assume that this is the node where the first balance is getting disturbed. Okay, let's say I had a node like this. If I had a node like this and the last inserted node is this node, assume the last inserted node is this node. If this is the last inserted node, I would get the -2 problem over here only, right? First time. So I would go
Yeah.
to the node over here, -2, and from here, from this node, I would check in which path I have to move, but only 2 steps, right? Only 2 steps I would check in which path I have to move in order to go to the direction where the newly inserted node is there. So in this example also, I would move right once, right? And then again at this node, in order to reach the node which is newly inserted, I would move right. Right? I would reach here. Now after this, I have to move left, but I am not considering anything. Only 2 things I have to consider. Only 2 times. So right, then again right. Right? That's the idea. If I would have my newly inserted node over here, then also it would be right and right, because this is the newly inserted. But if I would have my newly inserted node, let's say I had a node here, and my newly inserted node is, let's say, this one. Okay, so which is the first number which is getting unbalanced? Again, it remains the same, the 1 number, right? But now in order to reach this newly inserted node, I have to come right and then left. I am ignoring this right just 2 times. So right and then left. This left I am. So I would get, since I have only I am only 2 times I am checking, either right and 2 edges, right, in order to reach that path. So since I am checking 2 edges, I would only get 4 combinations: right, 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 left, left, right, left, left. These are the 4 rotations that you may have to use. I know you are getting confused now, but when I go to that example, you would understand. As of now, just understand how this RR, RL, LR, and LL rotations are coming. You insert a new node, you find from bottom to top the point where it is first violating the balance condition. From that node where it is first violating the balance condition, you check in which direction I have to move in order to reach the node which was newly inserted on the same path in which you reached. And you check only 2 times. So in this example, 1 right and 1 left. Then I reach over here, and further I have to move 1 more right to reach the newly inserted node, but I am not considering this because I would only consider 2 times, right, left. So that's why the concept is, in order to solve this unbalanced thing, this unbalanced tree, I have to apply the RL rotation. RL. So among these 4 rotations, I would apply RL rotation. What is RL, RR? All those things I would discuss. Okay? So RL rotation I have to apply. If the previous case would have been the scenario, if I would have inserted my new node over here or here or here, you know that I am only considering 2 steps, so it doesn't matter. Only it matters up to this level. So in that case, if either of these two are my new nodes, then I would apply R rotation, RR rotation. So which rotation to apply? That should be at this level. You should understand that. What are these 4 rotations? Forget about it. Which to apply? That you check by doing this step. Why? Is that part okay? Did you understand what I was telling?
Yes.
Okay. So RR rotation, RL rotation, LR rotation, LL rotation. Now, what are these 4 rotations? That is the next thing. The beauty is this RR rotation and LL rotation are the simple right and left rotate. The one that we have been doing till now. So that is already familiar to you. When you are moving right, so whenever you see this RR thing happening, now just tally it. Just again come. Just see what we did initially. In this skewness, when the skewness was directly like this, right? In this was something like this. We were making a simple rotation like this, right? A left rotate, simple left rotate. So this left rotation is nothing, is actually formally it is called your RR rotation. Because one right and then another right in order to reach the new node from the unbalanced node. From the unbalanced node, one right, then another right in the path of reaching the new node. So
It's
RR.
clear, sir.
Fine.
Yes.
Now these two are done. These two are new. And these two new rotations is what we would learn here. And accordingly, we know that it should be RL and LR, right? So if this is my unbalanced node, then this is R and this is L. And let's say if my new node is something over here or here, either of these two, then that is an RL rotation. I need a RL rotation to apply. So it should look something like that, and that is essentially is what it's happening over here. You see over here. What is the problem? 16 is the first node which is unbalanced. So what is the last node that I inserted? 17 is the last node that I inserted. In which path I have to travel from 16 to reach 17? First one R, then one L. So that's your RL rotation. Now what is an RL rotation? RR and LL rotation are simply right and left rotate. Okay. But what is an RL rotation? The thing is, now let's do that. RL rotation, as its name suggests, since they were RR and LL, they were both the same letters. So we only did simple rotations. Right? If it is RR, that means you would rotate towards left. Because RR means what? The skewness would be right. That's why you are getting right. RR. So that means you have to move towards left. So RR rotation means moving towards left or pulling towards left. LL rotations means pulling towards right. Only one. But here I have two separate, both R and L. So at first I would apply the L. That's why I said that I am not telling you on which node you have to do. You have to do the RR and LL rotation on the top itself, because there is only one rotation you need, right? If you need only one rotation, it doesn't matter. You can rotate it right by holding 19, by holding 16, anything. If you hold 16 and pull it down, then also the structure would something be like this. And if you hold 19 and pull it up, then also the structure would be like this. Intuitively, what do you get? Either you hold 19 and pull it right, or you hold 16 and pull it right. Both of the cases, the structure would come to something like this. So it doesn't matter in case of a single rotation. Single rotation means RR and LL rotation. But when you go for RL or LR rotations, which require you to do two rotations consecutively, then you do the first rotation from the bottom. All the work that we do in this tree is happening from bottom. We were finding the first unbalanced node from bottom, right? So all the thing that would happen is from bottom. So I would consider the lower one first. So LL. I mean, sorry, not LL, I mean the L. So if it is L, right? If it is skewed towards left, that's the meaning, right? RR means skewed towards right. So I apply left side. So left moving towards left is called RR rotation. So accordingly, if it is skewed towards left, I have to pull it
Right.
towards right. Exactly. So let's do that. 16. Pull it towards right. If I pull this thing right.
17. You get
Exactly.
17 and then 19. Yeah.
So now see, it is following the binary search tree property. Initially, when I pulled it in the other order, then it was becoming something like this, if you remember, which was our wrong. It's not following binary search tree property. But now this is following our binary search tree property. There is no problem. But again, if I do that, still the balance factor is not yet solved, right? Because you can see 10 and 2, I'm drawing up to this only. You see, this is what? 0, this is what? -1, this is what? -2. So even if I did one rotation, the balance factor did not solve.
But the
That's
advantage now we have is we got a one-sided screw. We got RR.
Exactly. We got RRs. That's the whole logic. Once you got RR, you have to just do this rotation, and
Right.
that's why this is R1. That's the whole intuition. So now you just do one more rotation in the other direction, and that is the meaning of R. R means skewed towards right,
When-
so you pull towards left.
When RL and LR are there, then two rotations are required, is it?
Two rotations, exactly. Fine. So now I would do this thing. So now this is my current tree, right? Only this part, but then I have 22 and this part. This part I'm not drawing because it remains same. So I have served this purpose. I have not yet served the rotation for R. So I would do that. So R means skewed towards right. R means right skewed. So rotate towards left. So rotate towards left. Do that and let's see what happens. So 16 would come here, 10 would come here, 2 would come here, 17 would come here, 19 would come here, and all other things remain same.
No, sir. Can you? 16 would come below. 17
Did I
would
make a
come
mistake?
there.
Wait.
Yes, sir.
No, fine.
Then I'm confused. I like to just see it again.
Wait. 16. So I'm drawing the first rotation, this L rotation
Yeah.
thing.
So there will be 17 and then 19. Yeah.
Okay. 10 was there, 2 was there. Okay. The other part I'm not
So-
drawing because that remains.
Yeah.
same.
So the problem is in 16 now.
Okay. So this is the problem. 16 is, we have the problem over here.
Right.
Okay. Now in which
Yes.
direction I would rotate it?
So I will rotate towards the left rotation. So 16 will be rotated to the left. Yes.
Yeah. Correct.
Now it's
correct. Okay. Acha. Oh, here I pulled the whole thing. No. Correct. Yeah. So this is the node, right? This is the node on which I would do the rotation. Always I told that the first node on which you are doing the rotation, that is the first unbalanced node. So 16 was the first unbalanced node. So on that I would do the rotation. Yeah. That's the thing. I pulled the whole chain down. So not from here. I would have done that if 10 would have been the first unbalanced node.
Right, sir.
Yeah. Fine. So so if I have this structure, and let us check for sake of correctness that whether it is solving the balance thing or not. This is balanced anyway. You can see this is a properly balanced kind of tree, and obviously here I have 2 and here I have 2 as well. So this is a balanced structure. So now this is my tree. And on that I would insert one more element. So up till how much we have done? 19, 17 is also done, 11 is the next element. So now let's insert 11 and see what happens. So 11 would be inserted where 10 is greater, 17 lesser, 16 is lesser, 11 is inserted here. So 17 is still fine, no balance problem. 10 is a balance problem, it would be minus 2. Right? Now since it is minus 2, which is again same step. So go to the first node where it is getting unbalanced from bottom, travel towards the same path in which you inserted the new node, and only consider 2 steps. So consider the first one which is right, consider the next one which is left, because I have to come to 11. So right and left. So this is a left, this is left skewed, so I must do it towards right side, right? So just rotate it right. What I would get is 10 to right. Here 17 would be
6. You'll get 16.
16. Yeah, so 16 L and R. So my 16 would go up, 17 would go down.
Go down.
Yeah. So 16, 17, 19, and your 16, 11. Fine. So always remember, I am first solving the problem which is at the bottom, the L, this L. If I'm so initially when we did the RR thing, right? When you had this node and then let's say this node, and let's say this node was minus 2. So what did we do? On this node it was minus 2. So we were solving the problem for this node and we were pulling it down. In this case, the problem is on this node, right? 16. At least this problem. I know the problem occurs from this, but I know that there are 2 rotations I need, R and L. So corresponding to this L, the problem is on 16. So at first I would do the rotation by holding 16 as the main pivoting point. So pull 16 towards right. Okay. So I pull 16 towards right, 16 comes here, 11 comes down, 17 and 19. But again I see that obviously the problem is not totally solved because I am still to do the right rotation here. So right means pull it towards left. Now on which node I have to pull, because 10 is the node on which this right is happening. So I would pull 10 down. Right? Right means right skewed, so pull towards the opposite direction, that is pull towards left. So if I do that, my graph would look something like 10, 2. Here 16 would come. Again, see, we would run into a finer problem here. 19 would come, but 16 had a left child 11, which I cannot place now with 16, but I can place it just like the previous case.
Previous, right.
So that's the whole thing. Now you can just repeat it. Same example, RL and LR rotation, whatever comes. Here I discussed RL, LR we have not yet seen, but the idea is same. If it comes, so let's say this node, then you have left, then you have a node, then you go right, and you have a node, and let's say this is your new node. Let's say here we had a node, and this is your new node. So the balance would happen over here. I don't think it's -2, it would be 2. Right? It would be 2 positive balance. So because it is left happening on the left side, so L and R. So if that is the case, okay, so how should I tackle it? At first I would tackle this one. If I have to tackle it, how should I do? This is right rotate, this is skewed towards right. So I must rotate it towards left. So in this direction I would do. So I would pick this and move it this direction. And then once that is done, again this left rotate I would rotate in this direction. Just like L, just the symmetric opposite of RL. Okay. The way we did here. So this example you can actually check on your own by, all the things are done, just you have to repeat it 1 or 2 more times and that should be enough. You will get how it's happening. I would request all of you to please do this LR-RL rotation on your hand at least 3, 4, 5 times until you get it correct for at least 3 times. Get it correct for 3 times. Once you get it correct for at least 3 times on an example, then it should be fine. Okay. So that was the whole thing of AVL tree, balancing, binary search tree, all the data structure part. The coding part is now left. Okay. Now, if you have understood the concepts well, then the coding part would be very easy to discuss. So the next session that I would take, I would discuss all the codings. Your min heap using both the algorithms, and along with that, the coding of AVL tree as well. And then we have the greedy. Greedy algorithms are quite easy. Only 2 things we have to discuss. So all those things I can manage in the next session. Okay, but please practice before the next session the AVL tree part. Your hand running of this AVL tree. Otherwise, the code would not be clear, because while if I do the code, I would not come to the theoretical part, because then I cannot finish all the topics. Okay. So yeah, do the code, do the concept properly. See what's happening in which case. Once it is done, the coding would be very easy. We are just writing the same thing, what we are doing in our mind, right? So that would be very easy. Okay, so thank you all.
Is that tomorrow?
Is there any preference for any of you?
Like when is that session coding for this?
We have not yet decided because. Okay, wait. So tomorrow anyway you have that programming session, and then Friday we have one more session.
Keep it in evening, sir. Please keep it in evening, sir.
Fine. So let's do this. On Friday, this Friday session, live coding we would not do. This Friday session, let me finish the whole thing. Okay. And live coding we would do on maybe Saturday or Sunday. Because that is anyway your practice kind of thing, live coding, but this is more of conceptual part. So your
Saturday, Sunday would be fine.
Saturday, Sunday we would take live coding. Friday we would take the open session. I would continue.
Okay.
Yes, sir.
Okay.
That'll be fine.
Okay.
Okay. And a request to all of you, since you know that we have to cover a lot of things in the next session. Not as this was a directly new topic, the data structure, how it works. But next day we would assume that all of you know all these things. So I would just go through the code and tell and recall that we did that rotation. That is actually we are writing in code by doing this. So conceptual example we cannot take. So please go through the example, solve it on your hand. Fine. I'm just requesting that you all of you do it. Thank you.
Thank you, sir.
Thank you, sir.
Thank you,
Thanks.
sir.
Thank you. Good night.
Good night.
Good night, everybody. Good night, everybody.
Good night.
Good night.